Okay, Chapter 7, Solving Exponential and Logarithmic Equations. The first lesson we're going to look at is on solving exponential equations. So in previous courses, you learned to solve exponential equations by writing the expression with the same base and then equating the exponent. So for example, if you had x exponent a equals x exponent b, because the bases are the same, then you can assume that the exponents have to be equal to each other. Okay, so in order for this statement to be true, the exponents have to be equal to each other. Okay. So exponential functions can be represented in many different ways by changing the base. So for example, you can take a number like 16 and you can write it with a base of 4. So it can be rewritten as 4 to exponent 2. Or you can take a number like 16 and write it to a base of 2. And so you can write it as 2 to exponent 4. So there's lots of different ways of changing a number so that it has a different equivalent base raised to a particular exponent. Oftentimes, it is useful to express the exponential expression or equation using a different base than the one that's already given. And so, for example, if you have a question like 2 to exponent x equals 64, it's difficult to solve this equation right now because the bases on the left side and the base on the right side are not the same. And so what you want to try to do is rewrite 64 as a power with a base of 2 so that you can actually compare their exponents. So, for example, what you would do is you would have 2 to exponent of x equals 64 is the same thing as 2 to exponent 6. And again, because the bases are the same, then that means that you can set the exponents equal to each other. The only way that this statement would ever be true is if the exponents were equal to each other. So there's a couple of different ways that we're going to solve exponential equations. One way is to try to solve an exponential equation by changing the base of one or more exponential expression. So looking at the left side and the right side, trying to get both of the bases the same. Sometimes you'll only need to change one of the bases. Sometimes you'll need to change both of the bases so that you can compare their exponents. Once the bases of the expressions on the left side and right side are the same, then you can set the exponents equal to each other and then solve for the variable that's missing using techniques you know from before. So we have a couple of examples here. And so these are exponential equations because there's an exponent that's involved, and the exponent is typically where the variable is that you're solving for. And so in order to solve these this equation, what I need to do is try to get the bases on the left side and the right side equivalent to each other so that I can actually compare the exponents. So I know that 729 is the same thing as 9 to exponent 3. So I can actually write 729 as a power with a base of 9. And so this would be 9 to exponent of 3. And since my bases are the same now, therefore my exponents have to be equal to each other in order for that statement to be true. And so I get x is equal to 3. So that one was relatively easy. Okay. For part B, same kind of idea. What you'll notice is that I have a base of 2 here and a base of 8 here. They're both exponential expressions, so this makes it an exponential equation. And so what I need to do is get the bases the same. This base is fine the way it is, and I know that I can write 8 as a power with a base of 2. And so I'm going to rewrite 8 to the exponent 2 as a power with a base of 2. So I'm going to rewrite that part. So the left-hand side stays the same, and the right-hand side changes to 2 to exponent 3 raised to an exponent of 2. Okay, so this is 8 written as a power with a base of 2. Now if I simplify the exponent on the right-hand side, I get 2 to exponent 6. And now you'll notice that since the base on the left side and the base on the right side, I have a single power here and I have a single power here, I can actually set the exponents equal to each other. So since the bases are the same, therefore x plus 1 has to equal 6, which means if I'm solving for x, x must be equal to 5. Okay, sometimes you'll get questions where it is not possible for you to rewrite each power using the same base. And so what we need to do is use a different technique called logarithms. So in order to solve some exponential equations, you will need to introduce a logarithm to help you solve for the variable. Okay, so this is looking at solving exponential equations where you have different bases. Okay, so to solve an exponential equation with only one term on each side of the equation, so you can only solve an exponential equation using this method as long as it's a single term like 5 to the exponent x equals 2 to exponent x plus 7. This is the only time you can actually use this method, when you have a single term here and a single term here. If you have something like 2 to exponent of x plus 2 to the exponent 2 equals 7 to the exponent x plus 1, something like that, you can't use this method for this kind of an equation because you have more than one term on one side. Okay, so this method only works when you have one term on each side of the equation. Okay, so what you would do in this case is you would take a common logarithm of both sides of the equation. So basically you're going to introduce a logarithm by taking the logarithm of the left side and taking the logarithm of the right side as well. And then what you could do is, you know that when you do have a logarithm, you can bring the exponent down by using the power law. And so that'll help you remove the variable from being in the exponent part of the equation. It makes your work a little bit easier. And then you can solve for the unknown variable. Okay? And so we're going to look at some examples of that as well. So we're going to look at solving some exponential equations where it is difficult to get the same base, so you can take the logarithm of both sides. Okay, so for example 2, we're going to solve each equation and we're going to leave answers in exact form. Exact form means no decimals. You shouldn't need your calculator. It's just a matter of rearranging the equation. Okay, so in this case, I have 5 to exponent t minus 1 equals 3.92. But what you'll notice is that I have a single term on either side of the equation, and that it's very difficult for me to either change 5 so I have a base of 3.92 or change 3.92 so that I have a base of 5. So instead what I'm going to do is I'm going to take the common logarithm of both sides. So I'll take the logarithm of the left side and I'll take the logarithm of the right side as well. And so what this will look like is log of 5 to the exponent t minus 1 equals log of 3.92. And now if I'm trying to solve for the variable, what you'll notice is that the variable is in the exponent part. And so what I'm going to do is use the power law and bring it as the coefficients. And so I get t minus 1 times, and I'm going to put t minus 1 in brackets because it's more than one term, times the log of 5 equals the log of 3.92. Now, at this point, because I'm trying to solve for t, there's a couple of different ways of doing this. The easiest way is, because I only have t in one spot, I can get rid of this log of 5 by dividing both sides by log 5. And so I'd be left with t minus 1 equals log of 3.92 divided by, divided by log of 5. And then to isolate t, I just need to add 1 to both sides. So I get t is equal to log of 3.92 over log of 5 plus 1. And now, because the question asks you for an exact answer, you would stop here. If it asks you for an approximate answer, you would type this into your calculator and get an approximate answer. Okay, and I think the answer is about 1.85 if you want to check it. Okay, let's take a look at the second example. It's the same kind of idea. I have a single power here and a single power here. And you'll notice that there's no way for me to write 8 as a power with a base of 3. And same thing here. I can't write 3 as a power with a base of 8. So because I can't get the bases the same, instead what I'll do is take the logarithm of both sides. So take the log of the left side, take the log of the right side. And so I get log of 8 to the exponent x plus 1 equals log of 3 to the exponent x minus 1. And same idea again, I'm looking for x, so I want to try to bring that down, and I'm going to use the power law of logs to do that. So if I bring it down here, I get x plus 1 times the log of 8 equals x minus 1 times the log of 3. Now in this case, it's not as simple as trying to isolate the variable here, because in part A, I only had one variable term. In part B, I have a variable term on the left side and a variable term on the right side. So I need to get all the x's on one side. The only way for me to do that is to actually expand out the x and the 1 on both sides, and then try to get all the terms with the x variable on the left-hand side, and then try to isolate it from there. So what I'm going to do is I'm going to use the distributive property and expand out the log 8 with the x and the 1 here. So I get x times the log of 8 plus 1 times log of 8 equals, same thing on the right-hand side, x times log of 3 minus 1 times log of 3. And now what I'm going to try to do is get all the x terms on one side and all the number terms on the other side. So I will move the x log 8 over to the right-hand side, and I'm going to move the negative log 3 over to the left-hand side. The only reason why I'm switching it in that order is so that I'm not dealing with too many negative terms. Not that it matters whether it's positive or negative, it just makes it a little bit easier when it's all positive terms. And so if I move this over and I move this over, I get log of 8 plus log of 3 equals x log of 3 minus x log of 8. And now from here, I'm trying to solve for x. And if it didn't ask me for the answer in exact form, I could write log of 3 and log of 8 as decimals and then combine the terms. But because it asks for exact form, what I'm going to do is common factor out an x, and then I can get rid of whatever is left on the right-hand side. So far now I have log of 8 plus log of 3 equals factor out an x and I get log of 3 minus log of 8. And now if I'm trying to get the x by itself, I just divide both sides by log of 3 minus log of 8. So if I divide both sides by that, I get x is equal to this entire thing. So log of 8 plus log of 3 divided by log of 3 minus log of 8. And don't try to cancel out any terms. You can't in this case, and that's because you have addition between the terms, so you can't simplify it any further, and that's your answer in exact form.